Hello, so there was a question to kind of give an overview of kind of the whole philosophy of hypothesis tests. So I'm going to give a quick, hopefully not more than like 15-20 minute review. So we have in these hypothesis tests, we have two hypotheses. The null hypothesis, which in symbolic representation is H0, and the alternative hypothesis is H1. This is going to be the hypothesis of the status quo, no change, or difference, just by chance. It's what we are believing to be true. Until evidence convinces us otherwise. Okay, your alternative hypothesis is the hypothesis you want to find evidence to support. Okay, these are both called claims. This is like the claim that you want, so it's going to be hypothesis or a claim that you want to find evidence to support. So here we have this word evidence in both of these. And the evidence is going to be your p-value. Okay? So your p-value down here is going to be the probability to get sample statistics at least as extreme as the ones you got, assuming the null hypothesis is true. Okay, so back in like chapter 8, when we were learning about sampling distributions, we found probabilities of a value or more extreme. Either is a value or more than it, or a value or less than it. Okay, and we did this by putting our proportion for the population as being a certain number, and that was my mu p hat, or our population mean was a certain value, and that was the same thing as our mu x bar. But we don't have that because we don't have a population proportion. We don't know that. All we have are sample statistics. So what we're going to do is we're going to assume that our mean of our population or our proportion of our population is going to be our null hypothesis. Whatever we're saying in the null hypothesis, we're going to assume is true. And we're going to say, okay, now we have sample data. How likely was it to get the sample data? If it was really, really unlikely, then we have evidence that maybe this null hypothesis isn't true anymore because it's not very likely to get this sample statistic, assuming that is true. Okay? If our evidence, you're like, that's not so unlikely, then we don't have enough evidence to believe the alternative hypothesis. So what we have here is our conclusions are going to be based off of our p-value. Is our p-value small enough? Is this probability unlikely enough that we believe that our null wasn't true or not? How we determine this is we compare it to our alpha, our significance level. I'm going to add to this in a second, but this is what we're going to say, okay, if our p-value is less than our significance value, then we are going to reject H0. If our p-value is greater than or equal to our significance value, then you're going to fail to reject. Or I think they say in the book, sorry, they say in the book, do not reject. Do not reject H naught. So think about what this means, because all we're gonna do is we're gonna make our conclusions based on whether we think H naught is true or not. If we reject H naught, that means we are like throwing it to the curb. We don't like it anymore. Like, kind of like you're rejecting your girlfriend or something like that. You aren't gonna be with her anymore, okay? So if you reject your H naught, that means you don't think that it is true. Our evidence suggests, because our p-value is less than our alpha, that it's really unlikely to get the sample statistic, assuming that the null was true. So we're going to reject what we assumed was true, okay? If our p-value is not as small as our significance value, then you do not reject it because you don't have enough evidence to convince yourself that it was hard to get that sample statistic, okay? So once you reject your H naught, that means that we have sufficient evidence to conclude that H1 is true, okay? If you do not reject H naught, then you have insufficient evidence to conclude H1 is true, okay? But this is just a probabilistic evidence, right? You don't ever actually know if you're totally right. Could we be wrong in our conclusions? Yep, we definitely could, okay? Because all we have, just because something is unlikely to happen doesn't mean that it's not going to ever happen. It could possibly have happened, right? So your type 1 error, is when you reject H naught, but you were wrong. And you shouldn't have. Okay? Because in actuality, in actuality, H1 wasn't wrong, so you shouldn't have rejected it. But our evidence gave us the scenario that we should reject it, okay? A type 2 error is when you do not reject H naught, but you were wrong. And you should have rejected. So, yeah. So up here, you were wrong and you shouldn't have rejected. And here you were wrong, but you should have rejected. H naught. Okay, so those are my two different errors. There's also a possibility that you were right. Maybe when you rejected H naught, you were correct and you really should have done it. Maybe when you don't reject H naught, that was right. You shouldn't have rejected H naught. So there's 4 possibilities. So in your conclusions, are you going to be rejecting H naught and do not reject H naught? And then we have, in actuality, H1 is true. Well, H naught is true and H1 is true. In actuality, we never actually know this. So there's always a chance that we are wrong because we don't actually know what's happening in actuality. All we have is the sample information, okay? So if you reject H naught and H naught was true, that means you're making a type 1 error, okay? Because you rejected H naught, but you shouldn't have, okay? If you reject H naught and H1 is true, you were correct. If you do not reject H naught and H naught actually was true, good job, you were correct. If you do not reject H naught but H1 actually was true, you have a type 2 error because you do not reject H naught but you were wrong and you should have. Okay? So let's kind of go through, see this in practice. It's moving, so let's go like this and go like that. Okay. A simple random sample of size n equals 40 is drawn from a population. The sample mean is found to be 108.7. The sample standard deviation is found to be 21.8. Okay. Is the population mean greater than 100 at the alpha equals 0.025? Okay. Level of significance. Okay. So we go through and we have our n is 40. My sample mean, which is x bar, is 108.7. My sample standard deviation, which is x, is 21.8. My two hypotheses are, we're dealing with a mean, so we're going to be the population mean, because our hypotheses are about our population parameter. The population mean of greater than 100. That's the claim that we want to find evidence to support. So our null is of no change, that there is actually, it is 100. It is 100. Okay. The claim is that we want to be greater than 100. Okay. So we go through, and with this information, we go to our calculator. You go to stat, go over to calc, go down to the t-test. The t-test is done for when you are doing hypothesis tests for a sample mean. We're going to do stats because we have the stats already given to us. Our mu naught is going to be the mean in our null hypothesis, so it is 100. My x bar is my sample mean, 108.7. My Sx is my sample standard deviation, which was 21.8. And my n is my sample size, which is 40. Then we have to go through, and this next line is going to look just like your alternative hypothesis. It says that my mean, and I want it to be greater than this mu naught that was in the hypothesis. You have to move this over here and highlight that box. And then push calculate, and you get this. Okay, so this t is your test statistic. So we have a few things here. We're going to kind of make it so I can see everything at once. So we have let's close this help. Okay. Oh my goodness. Okay. So we had our output here is our t. This is going to be our test statistic. and that is going to be 2.52. P, that is my p-value, and that is 0.008. And then it just restates your x bar and your sx and your n for you. Okay, so for work, you would say this, and you'd say that mu is greater than mu naught. Okay, this would be showing your work because it's telling me the function that you're using and the inputs into that function. Okay, so we're going to go through and we're going to kind of talk a little bit what a test statistic is. Okay. Oh, cancel. So we can go next page. Okay. So now that we have that, then what does this actually mean? Okay, so we have all that we need to be able to get our answer and be able to make a conclusion. Okay, my alpha at first was 0.025. My p-value was 0.008. This is smaller, so my p-value is small, so p-value is low, so my h naught must go, so I'm going to reject h naught. Okay, this means that I have sufficient evidence that, and then the alternative hypothesis was that, oh, it disappeared. Oh, no, it's right there. Is that my population mean was greater than 100. So that the population mean is greater than 100. Okay. However, I also asked you to look at when the level of significance was 0.005. My p-value still is the exact same, and now my p-value is greater than that. So here I would fail to reject h naught. This rejection just depends on what this alpha is. Okay, so you would say in this case, I have insufficient evidence the population mean is greater than 100. Okay, so alpha is a significance level, and if you think about it, I'm going to add to the definition up here that alpha, I told you up here, was your significance level, but it's also, oh my goodness, it also is the probability of making a type 1 error. Okay, it's going to be the probability that I'm okay with making a type 1 error. Okay, so if it would be a really, really bad consequence to make a type 1 error, then I would make my alpha really, really small, because then I would never ever fail to reject my h naught. Okay, because type 1 errors are when I reject h naught but I shouldn't have. But if I really think that it's going to be a bad mistake to reject h naught, then I want to make that alpha really, really small, because I want that probability of making that type 1 error to be really, really small. However, if I make alpha really, really small, then I'm going to have a higher probability of making a type 2 error, because going to be less likely to reject H naught because I'm going to have fewer probability of making a type 1 error. And so then I'm going to have more chance of being wrong because I didn't reject H naught. Okay? Hopefully that makes sense. Your test statistic has to do with your sampling distribution. Okay? So remember what we're happening here. We are assuming this mean was 100 because we had from chapter 8 mu x bar is going to be the mu that you're assuming to be true, which is 100. Your sigma x bar is going to be your s divided by the square root of n, which is 21.8 divided by the square root of 40, which is 3.4. Okay, so we're saying that if I went up one standard deviation, it would be 103.4. Okay, I went up 2 standard deviations, then it would be 103.4 plus 3.4, which would be 106.8. You go up one more standard deviation, and this is actually not exactly the same as what it was in chapter 8, and that's why we are using the t distribution instead of the z distribution, because we're going to have more area in the tails. So I go one more, it's going to be 110.2. So my value of 108.7 is like right there, which is about 2.5 or 2.52 standard deviations above it. So the probability of being at least this extreme, that's your p-value. Okay, 0.008. The area of the shaded value of this sample statistic or more extreme. Okay, so hopefully that makes sense. It was kind of the whole theory all at once, and good luck.